Ever wonder what happens after you swallow that pill or get that injection? Like, how does this tiny thing have such a huge impact on your body?
Yeah, it's pretty amazing, right? The journey a drug takes through your system is fascinating.
Definitely fascinating and probably something most people don't think much about.
hmm
And it's not like it's easy to figure out on your own.
No, not really. But luckily, there's a whole field of study dedicated to it.
And that is,
Pharmacokinetics, often shortened to PK for obvious reasons.
right, PK. So we've done a deep dive into the research here to break it all down.
Yeah, basically what your body does to a drug.
From the moment it enters to, well, the moment it exits, and why that's so important to understand, not just for doctors, but for all of us.
Absolutely. Because knowing this helps us make sure that the right amount of medicine is getting to where it needs to go to do its job.
Safely and effectively.
Right. And to understand PK, we often use this handy acronym ADME,
ADME.
which stand for absorption, distribution, metabolism, and excretion. Each of those is a crucial step in the drug's journey.
Okay, so let's start at the beginning. Absorption. What actually happening there?
So absorption is basically how a drug gets from wherever you took it into your bloodstream.
Okay.
Simple enough.
Well, kind of. The way you take a drug plays a huge role here. You know, if you get an IV, it's a direct line into the bloodstream.
Yeah, it bypasses all that absorption stuff, right?
Exactly. We call that 100% bioavailability, meaning all of the drug gets into your system.
But pills are different.
Oh, yeah, definitely. Pills and other oral medications, they've got a much longer and more complex path.
There's a whole obstacle course in there.
That's one way to put it. The pill has to break down. The drug has to dissolve. It has to survive the sometimes harsh environment of the stomach.
All that acid.
Right.
Yeah.
Then it has to get absorbed through the walls of your gut and into the bloodstream.
Sounds like a lot can go wrong.
Oh, it can. And all sorts of factors can influence this process,
Yeah.
like the drug's formulation. Is it a tablet, a capsule, a liquid?
And I imagine the properties of the drug itself matter too. Hugely. Like how soluble is it in water or fat? What's its PK? Those all come into play.
Yeah.
It's a measure of the drug's acidity. Basically how it interacts with, different pH levels, like the pH in your stomach.
Oh, right. So, like, does it break down more easily in an acidic environment or not?
Exactly. And even things like how quickly your stomach empties can affect absorption.
Wow, so many variables. Does it matter if you take a pill with food or on an empty stomach?
Absolutely. Food can sometimes help absorption, but it can also hinder it. It really depends on the specific drug.
So I guess this is why doctors are always so specific with instructions like take with food or take on an empty stomach.
Exactly. And then there's another big hurdle for oral drugs, and this one is particularly interesting. It's called first-pass metabolism.
First pass metabolism.
So this is where, before the drug even reaches the rest of your body, a good portion of it gets metabolized, broken down,
By.
enzymes, mainly in your gut and liver.
So basically, some of the drug is lost before it can even do its thing.
Right. It's like, imagine you're sending a package, and before it even gets to its destination, some of the contents get removed at a checkpoint.
A drug toll booth.
Yeah, kind of like that. That's why you often need a much higher dose of an oral drug to achieve the same effect as, say, an IV dose of the same drug, because of that first pass loss.
Okay, that makes sense. And that all ties back into bioavailability, right?
Exactly. Bioavailability is basically the percentage of the drug that actually reaches the bloodstream.
After running the gauntlet.
Yeah. It's often represented by the letter F. So a drug with an F of 1 means 100% bioavailability.
Like with IV administration.
Right. But with oral drugs, F can be much lower, sometimes only 10% or even less.
Wow. So figuring out the right dose for oral medications, that must be pretty complex.
It is. You have to consider all these factors to make sure you're getting enough of the active drug into the system.
Okay, so let's say the drug has made it through absorption. It's in the bloodstream. Where does it go next?
That's distribution. The drug starts moving out of the bloodstream and to the different tissues and fluids of the body.
It's spreading out.
Right. And to understand how it distributes, we talk about the volume of distribution, or VED.
What does that tell us?
It gives us an idea of how much the drug likes to stay in the bloodstream versus going into the tissues.
Okay, so a high VED means?
It means the drug prefers to leave the bloodstream and hang out in the tissues.
So the drug is like, bloodstream's boring, I'm going exploring.
Haha, exactly. And a low VED means it's more content staying in the blood.
So what determines where a drug goes? Like, why does one drug end up in the brain and another ends up, I don't know, in the muscles?
Several factors. One is tissue permeability. Basically, how easy it is for the drug to cross cell membranes.
Some tissues are easier to get into than others.
Right. And the drug's properties affect this. Like if it's lipophilic, meaning it dissolves easily in fat, it can cross certain barriers
Ah,
more easily.
so like the blood-brain barrier.
Yeah.
That's notoriously difficult to get through.
Exactly. That barrier is designed to protect the brain from harmful substances. But some drugs need to get into the brain to work. So designing drugs that can cross that barrier, it's a big challenge.
Makes sense. Are there other barriers like that?
Yeah, the placental barrier, protecting a fetus.
Right. Very important.
Yeah.
What else influences distribution?
Something called plasma protein binding. This is where drugs can bind to proteins in your blood, like albumin.
And what does that do?
Well, only the unbound drug is really active. The stuff that's bound to protein is basically out of commission.
Okay, so it's like a reserve pool.
Kinda. This can get tricky because different drugs can compete for those binding sites. One drug might kick another drug off its protein, making more of that second drug active,
Leading to.
potentially stronger effects,
Mhm.
or even side effects. Warfarin, a blood thinner, is a classic example of a drug that's highly protein-bound and prone to these interactions.
Okay, so protein binding, it's like a delicate balance.
It is. And then the final factor influencing distribution is simply blood flow.
The circulatory system.
Organs with a rich blood supply, like the brain, liver, and kidneys, they get the drug delivered much faster than tissues with less blood flow.
Makes sense. Okay, so the drug is distributed. It's reached its destination. What happens next?
Next up is metabolism.
Yeah.
This is where your body starts chemically modifying the drug, basically transforming it.
And why does it do that?
The main goal of metabolism is to make the drug easier to eliminate from the body
And how do they do that?
by making it more water-soluble, so your kidneys can easily filter it out.
Okay, makes sense. So where does this metabolism mainly happen?
The liver is the major player here. It's like the drug processing plant of your body.
And what happens in this processing plant?
Well, there are two main phases of metabolism. Phase 1 often involves introducing or exposing functional groups on the drug molecule.
Functional groups?
These are specific groups of atoms that make the molecule more reactive. And this often involves enzymes called cytochrome P450, or CYP450 for short.
CYP450. I've heard that before.
They're a super important family of enzymes. They can do a lot of things. They can activate a drug, making it more potent, or they can inactivate it, or sometimes even create toxic metabolites.
Toxic metabolites? That doesn't sound good.
Yeah, sometimes metabolism can produce byproducts that are actually harmful to the body, so it's a double-edged sword.
So it's not just about making the drug easier to excrete, it's also about changing its activity.
Right. And then phase 2 of metabolism involves conjugation reactions. This is where another molecule gets attached to the drug, making it even more water-soluble.
Okay, so phase 1 tweaks it. Phase 2 slaps on a big water-loving tag, ready for disposal.
Exactly.
So what influences how our bodies metabolize drugs? I imagine that varies from person to person.
It does, and there are a few key factors. First off, your liver function. If your liver isn't working properly, it can't metabolize drugs as efficiently.
Leading to?
The drug can build up in your system, leading to potentially dangerous side effects.
So people with liver problems, they often need lower doses of medication.
Right, and then your genetics also play a big role.
Our genes.
Yeah, remember those CYP450 enzymes? Well, we all have slightly different versions of those enzymes due to genetic variations.
So some people might have super efficient CYP450s, while others have slower ones.
Exactly. And that's why the same dose of a drug can have very different effects on different people. Some people might metabolize it very quickly, so they need a higher dose to get the desired effect. Others might metabolize it very slowly, so a standard dose could be too much and cause side effects.
Wow, so it's not one size fits all.
Nope. And this is why personalized medicine is becoming so important. Tailoring treatment to an individual's genetic makeup.
Okay, what else affects metabolism?
Drug interactions. Some drugs can actually mess with the activity of those CYP450 enzymes.
So taking two drugs together could, either boost or dampen the effects of one of them?
Exactly. We call these drugs either inducers or inhibitors.
Inducers speed things up.
Right. They increase the activity of the enzymes, which means the drug gets metabolized faster and might not be as effective. Rifampicin, an antibiotic, is a classic inducer.
And inhibitors.
They slow down metabolism, so the drug stays around longer and could potentially lead to higher drug levels and even toxicity. Erythromycin, another antibiotic, is a good example of an inhibitor.
Okay, so this is why it's so important to tell your doctor about all the medications you're taking.
Absolutely. They need to be aware of any potential drug interactions to avoid problems.
Makes perfect sense. Okay, so the drug's been metabolized, made more water soluble. What's the final step?
Excretion, getting that drug and its metabolites out of the body.
Show's over. Time to go.
Exactly. And the main route for excretion is through the kidneys. They filter your blood and remove waste products, including drugs.
They'll pee it out?
Basically, although the liver also plays a role. It can excrete some drugs into bile, which ends up in your feces.
So you can poop it out too.
Right. And there are other minor routes of excretion, like through sweat, breath, even breast milk. But the kidneys, they handle the bulk of it.
Okay, so are there any factors that affect excretion?
Definitely. Just like with metabolism, your kidney function is crucial. If your kidneys aren't working well, drugs can build up, so dosages might need adjusting.
I imagine that's a big concern for people with kidney disease.
Absolutely. And liver function also matters for drugs that are excreted in bile. And even the pH of your urine can affect how easily some drugs are reabsorbed back into the bloodstream.
Okay, so ADME, absorption, distribution, metabolism, excretion. This whole journey is a lot more complex than I ever realized.
It is, and it really highlights why it's so important to get the right medication and the right dose for your specific situation.
Because there are just so many variables at play.
Right. Things like your age, your weight, your genetics, your overall health, other medications you might be taking. It all affects how a drug moves through your body.
And understanding these factors, that's what helps us make sure that medicines are used safely and effectively.
Absolutely. It's all about optimizing drug therapy, getting the most benefit with the least risk.
And two important concepts that tie into all of this are clearance and half-life, right?
Yes, clearance refers to how efficiently the body eliminates the drug. It's basically a measure of how much blood is cleared of the drug per unit of time.
So a high clearance means
The drugs are moved from the body quickly, and a low clearance means it sticks around longer.
and half-life.
That's the time it takes for the concentration of the drug in your blood to decrease by half.
So a drug with a short half-life, you need to take it more often to keep those levels up.
Exactly. And a drug with a long half-life, you might only need to take it once a day or even less frequently.
So all of this, ADME, clearance, half-life, it's all interconnected.
It is. It all paints a picture of how a drug behaves in the body, how it gets in, where it goes, how it's processed, and how it gets out.
This whole conversation has been really eye-opening. It makes you think, like, even though we might not see it, there's this incredible complex journey happening inside us every time we take a medication.
I agree. And the more we understand about that journey, the better equipped we are to make informed decisions about our health.
Absolutely. So next time you pop a pill or get an injection, think about all the amazing things happening behind the scenes to get that drug where it needs to go. And appreciate the science that makes it all possible.
I completely agree.
It's fascinating stuff. Thanks for breaking it all down for us.
My pleasure. Always happy to shed light on the world of pharmacokinetics.
And for our listeners, if this deep dive has sparked your curiosity, there's a whole world of information out there, so keep exploring and learning. And remember, the more you know about your body and how it interacts with medications, the better you can advocate for your own health. Thanks for joining us today on The Deep Dive.